Hi everyone and welcome back. We are now up to tutorial 6 and we're going to be finishing off one-way Anovas today. So last week we looked at independent samples t-tests and we looked at Anova as well. And we spoke about Anova being an alternative to independent samples t-tests when your IV has more than 2 levels. And we said that Anova is useful in this case because it can compare 3 or 4 or 5 or however many levels you have of an IV together simultaneously without having to run multiple tests, without producing multiple p-values, without inflating your type 1 error rate, without increasing your chances of telling a man that he's pregnant. And last week we did our Anova, our one-way Anova, and we kind of waved it in your face and said, look, this is a one-way Anova, isn't it beautiful? But we didn't really take it that step further and actually go, so if we do have a significant effect and we do need to figure out where that difference lies, how do we do this? And so that's what today is all about. So I'm going to load up my data set, looking at the coaching data this week. Isn't it good when data works? Okay, it's loading. So let's go and look at the data set. We have 2 variables, feedback and miss. So the data set that we're looking at this week is trying to determine whether or not the number of misses made in a basketball game can be predicted by the type of feedback that a team receives. We have a single question. How do various coaching styles impact a player's performance on the basketball court? Now, what's interesting is that there's no direction. Now, we spoke about this last week in terms of t-tests because you look at a 2-tail or a 1-tail depending on whether or not there's direction. Now, what we're actually interested in is whether or not there's a hypothesis. And here we have a question. How do various coaching styles impact players' performance in the basketball court? There's no expectation that they will. There's no expectation of a particular direction. There's no expectation that one style is better than another. There is simply the blanket statement, is there a difference? So there's no real hypothesis. What this means is we have what's called a post hoc design, or a design in which hypotheses will be derived after we've looked at the means. So, post hoc design, no hypotheses. This is absolutely crucial. It's really, really important to know that from the research question alone, we know if a design is post hoc, or if it's a priori, or sometimes that's called a planned design, and that's where we have hypotheses. So it seems kind of arbitrary at this point to have fancy words that basically mean do I have hypotheses or not, but we'll see later on why it's so absolutely vitally important that we know whether or not a design has hypotheses, and more to the point whether or not that means we have a post hoc or an a priori or a planned design. So just to recap, this study does not have hypotheses, it only has a research question, so we have a post hoc design. The sampling population is elite college basketball players from 3 different universities. And this is taken directly from the summary that you guys have. The data summary, so we have 1 DV, it's the number of missed 3-point baskets. It is called miss and it's numeric. And we have 1 IV called, and this is the type of feedback that a group received. It's called feedback in our data set. It's represented in long format. So that means we have a single column for feedback that has all the different levels underneath it. It's categorical. It's technically nominal. So what this means is that there is no particular order. I could change the order around. It doesn't tell me anything different. I have 3 levels and it's between subjects. So just a reminder that between subjects means that each person was allocated to 1 feedback group. They didn't go through all 3. They only went through 1 feedback group. So if I bring this together, we have an experimental design. So we're manipulating the type of feedback that a group receives. The research question involves comparing more than 2 groups of 1 categorical level IV together. 1 categorical IV together. The DV is numeric and the IV is categorical. So a one-way Anova is the most appropriate hypothesis test. We're going to very quickly go over our assumptions. So this is the same syntax that we used last week, just changing it for the variables that we're looking at this week. I'm only going to do this very quickly. I have an error. Vector variable and time series operators not allowed. Ah, I didn't have the comma there. I made this mistake last time. Let's try that again. So looking at my histograms, it looks like group 1, which if I look back here, level 1 is my praise feedback group, seems to have a positive skew. Level 2, my criticism feedback, looks very platocodic. Level 3 is probably the most normal out of all of them, but it still looks very platocodic as well. Let's see what the numbers say. I have a mean of 4.5 missed baskets for my praise group, 7 for my criticism, and 5.9 for my no feedback group. My standard deviations all look pretty close together. My skewness, I can see that positive skew for my praise and my criticism group. And interestingly, there's a suggestion of a negative skew in my no feedback group, despite the fact that it looked pretty normal. For ketosis, we can see that it is looking quite platocodic for my praise and also for my, my criticism group. And the most normal out of the three is my no feedback group, which kind of makes sense. That reflects what we saw in the histograms. Okay, so not the best in terms of normality, but it's not the end of the world. Let's check out equal variance. So again, we did this last week, so very quickly just going to look at this. I'm looking at W0 and I can see it's non-significant. This tells me that within a margin of error, my standard deviations are basically the same. They're near enough. We're happy with this. So we can now proceed to our Anova, reminding ourselves that an Anova will give us a single p-value that tells us whether or not our dependent variable changes across our levels of our IV. So whether or not there is a difference in our dV across the levels of the IV, but it won't tell us where that difference lies, just that there is a difference. And so our null hypothesis then is that the mean of group 1 will be the same as the mean of group 2, is the same as group 3, group 4, and so on. So if I took the differences of all these groups, it'd equal 0. Now something that I didn't mention last week, this Anova model that we're fitting, this big table, it's called an overall Anova model or an Omnibus Anova model. And you'll hear about this all the time. I'll be referring to them as overall and omnibus models. We can see we have 30 participants in our study. That makes sense because each of our groups have 10 people. My R squared is 0.42, so 42% of the variance, or 41.98% of the variance. And the number of baskets missed can be explained by the type of feedback that a group got. Again, my model line is the exact same as my feedback line. Next week, when we move into two-way, we'll see that this is not the case. I have 31.4 units of sums of squares for feedback, 43.4 for residual. That totals to 74.8. 31.4 divided by 2 would give me 15.7. And my residual sums of squares divided by its degrees of freedom would give me 1.61. If I divide my mean sums of squares for feedback by residual, I will get 9.77. And if I was to calculate the probability of obtaining an F of 9.77 on 2 and 27 degrees of freedom, if my null hypothesis was true, if there was no difference, the probability of that would be 0.06% of a chance. Now we defined sufficiently unlikely as 5%, or we define significance as a p-value less than 0.05, so this is a significant effect. So this tells me that in the population, the type of feedback that a basketball player receives does seem to be related to the number of misses that they will make. However, we don't know exactly where the difference lies. So because of this, second stage analyses are justified. And when I'm writing up my conclusion for my Anova, because you need a statistical and a real-world conclusion for your Anova, I would state that second stage analyses are justified.